Welcome back. So now we're going to look at a few equations that you'll come across in level 2 physics and how they're connected to each other and some of the different meanings behind them. So part A, using F net equals mass times acceleration, so Newton's second law of motion, and AC, so centripetal acceleration, equals v squared divided by r, derive the formula for centripetal force. So a reminder, centripetal force is not a force, it is a net force. And we know that net force is equal to mass times acceleration. Well, in circular motion, the acceleration, AC, the centripetal acceleration, is inwards. The net force must therefore also be inwards, so F subscript C. And we can combine these two formulae to derive the equation for centripetal force. So substituting in centripetal acceleration in for acceleration in Newton's second law, it would become mass times v squared over r. And when we have like m times this fraction, it's the same as writing it as mv squared divided by r, where m is the mass in kilograms of the object undergoing circular motion, v is the speed about which it is going in that circular motion, and r is the radius of that circular path. Right, so all as we did was substitute centripetal acceleration in for A in Newton's second law of motion. Alright, and B, show that F equals ma is equivalent to F equals change in momentum over change in time when mass is constant. Okay, so again, Newton's second law that we're familiar with. Looking at this one, it is actually rearranged as change in momentum is force times change in time. So that's the impulse equation. And Newton's second law and change in momentum over change in time are actually the same thing under certain conditions. So let's investigate that. So F equals ma, and F equals change in momentum over change in time. Cool. So in class, you've been learning about Newton's second law since year 9. However, Newton's second law is more accurately described as the change in momentum over the change in time. The reason for that is because mass isn't always constant. For example, a rocket, right, expelling fuel, it's losing mass, but it still is producing a force upwards, so its mass is not constant, which is why using change in momentum lets us describe that as well. So how do we connect these two? Well, what's the equation for momentum? Mass times velocity, right? And now it's said for a fixed mass, a constant mass, but velocity could still change, right? So change in momentum is mass times change in velocity. Now substituting that into F equals change in momentum over change in time, we get F equals mass times change in velocity, right, which is change in momentum for a constant mass, over change in time. And now what's our last step? So I see we have mass, but we're missing acceleration. Well, look at that. Change in velocity over change in time is acceleration. Therefore, F net is equal to mass times acceleration. Alright, so we've connected F net equals mass times acceleration and F net equals change in momentum over change in time by the momentum equation, mass times velocity, and the acceleration equation, change in speed over change in time. But more commonly in level 2, you will see this equation coming up in collision scenarios, right? Change in momentum or impulse. So you throw a ball against a wall. What is the force the wall exerted on the ball if the collision was 0.1 seconds? Things like that. All right, and C. The equations for torque and work appear to be the same. So on your formula sheet, there are both force times distance. How are they different? So at first glance, they look the same, but we know that torque has to do with applying a force some distance from a pivot point, right? Rotational force. And we know that work done is, let's say, you pushing an object with some force, some distance. And in doing so, you have transferred energy to the object. So in this example, if you're pushing something along the ground, you're giving it kinetic energy. So how are these scenarios different? So starting with work, we notice that the force applied is parallel to the displacement, right? Parallel to the direction you are pushing it. So we could say force and distance, or displacement because it's a vector, are parallel. Yeah, or in the same direction. Conversely, for torque, the force applied is perpendicular to the displacement from the pivot point. So we'd write F and D are perpendicular. Right, where F and D are both vectors, so they have direction and they are perpendicular to each other. Yeah, and that is the difference, right? Extra for experts, torque is actually what's called a cross product, and work is what's called a dot product. So cross product and dot product. And these are ways of multiplying two vectors. So depending on if you're multiplying them when they're like in line with each other, when they're parallel, it would be a dot product, and it results in just a scalar, so an amount, whereas a cross product results in an amount and a direction. Yep, so you can look that up if you like. In sort of first year university in physics, you'll learn about this in the mathematics courses as well. Part D, explain the significance of the negative sign in Hooke's law. So what does this negative sign mean? Well, before that, we know that Hooke's law tells us the force required, so force to stretch a spring or a spring-like object some distance, and they are connected by the spring constant. Right, you could have soft springs that are very easily stretched, they require little force, or you could have very hard springs that require a lot of force to stretch or compress. But why is there a negative sign? So let's draw a diagram. Beautiful spring. If you pull the spring out, so to the right, with some force F, the spring is going to resist that force with what's called a restoring force. And that force acts in the opposite direction to the distance that you pull it, right? The spring's going to want to bounce back. You're pulling to the right with your own force, green F, right? You're pulling it to the right with some force, that in this case is green, right? Fu, okay, maybe not, no, that's not good. The green F, right? You're pulling it to the right. Now the spring is going to want to pull it back to the left, which is why we use the negative sign to show that the restoring force of the spring, restoring force, is opposite to the direction of the displacement, or the distance you are pulling it. Similarly, if we had the same spring and you were pushing the spring inwards, you were compressing the spring, so its distance will be going now to the left, the spring is going to want to bounce back and restore itself to its equilibrium position. So the spring is providing a force to the right, which is opposite the direction that you pulled it. Right, and that's why we have that negative sign. For calculations, like finding the spring constant is always going to be positive, so we often just ignore that if we're given a force and a displacement. And that's because the force we're often given is this force. It's the force applied on the spring, it's not the force the spring fights back with. Right? So once more, in calculations, if you end up with a negative spring constant, don't stress. What that means is you took the wrong force, and you can just omit the negative sign. But the meaning behind it is that the force the spring fights back with, like the restoring force, is opposite to the direction of the displacement. Alright, and finally, part E, derive all of the kinematics equations. So I'm not going to do that because that's going to take me way too long. However, I found a very good article for you to look through. But let's just do the first one together, and then have a think about how you could derive the rest. But anyway, you can look that up afterwards. Part E. So we know acceleration is change in velocity over change in time. I hope, right? And we know that change in velocity is the final velocity minus the initial velocity. Vf minus Vi. So I can replace in the acceleration equation change in velocity with Vf minus Vi over delta t, right, or just t. I can multiply both sides by t, and I can add Vi to both sides. And that is one of our kinematics equations, right? Vf equals Vi plus At. There we go. So that's one of the processes for deriving this particular equation. The other ones follow a similar pattern using the foundational motion equations. Right? And then once you have a few kinematics equations, you can actually use those to derive new ones as well. So I encourage you to give it a go. And once you've given it a go, you can have a look online at this article, Physics Way, Deriving Kinematics Equations. Alright, I will see you next time.